Now we move on to the normal distribution, which is perhaps the most important distribution, and we will spend a fair amount of time on this. This is what a normal distribution looks like. It is sometimes called a bell-shaped distribution. We have a certain mean value denoted by mu, and the random variable is distributed around that mean value. A normal distribution is denoted using these symbols. So x is the random variable, n stands for the fact that this is a normal distribution. Any normal distribution can be defined based on the mean value or mu and the variance of that normal distribution. Knowing the variance is essentially the same as knowing the standard deviation. So if I say that x is a normal distribution with mean 10 and standard deviation of 2, i.e. variance of 2 squared, then we are completely defining a particular distribution. A normal distribution will have skewness of 0. That means that the distribution is completely symmetric. The amount of data to the left of the mean is exactly equal to the data to the right of the mean. In fact, the distribution to the left is essentially a mirror image of the distribution to the right. So that means that skewness is equal to 0. And something that you just need to memorize, kurtosis, which is a measure of how peaked the distribution is, and a measure of the tails is 3. So just by definition, the kurtosis of a normal distribution is 3. There is some basic information that you need to memorize related to a normal distribution, and I'll just share that with you over here. Approximately 68% of all distributions fall in the interval mu plus or minus 1 standard deviation. In the example that I just talked about, let's say that the mean or mu is 10, and if I said that the standard deviation is equal to 2, then what we are saying is that if the total area under this curve or total probability is equal to 1, then 68% of the data will fall within 1 standard deviation of the mean. 1 standard deviation is equal to 2 in this particular distribution. So 1 standard deviation will take us to 12 on the right side of the mean and 8 on the left side of the mean. So this total area is 68% of the total area under the curve. In other words, 68% of the data will lie between 8 and 12. So this is a continuous random variable which spans from minus infinity to plus infinity, and 68% of all this data will lie between 8 and 12. Approximately 95% of all observations fall in the interval mu plus or minus 2 sigma. Again, with sigma equal to 2, so 2 sigma gets us to 14 over here, and 10 minus 4, which is 6 over here. So we are saying that between 6 and 14, we now cover 95% of the data. And this is also fairly obvious looking at the picture, that if you have 100% of the data between minus infinity and plus infinity, then 95% of the data is covered if we go from 6, which is 2 standard deviations to the left of the mean, till 14, which is 2 standard deviations to the right of the mean. And finally, for this slide, approximately 99% of all data will fall within 3 standard deviations of the mean. Next, we move to the concept of confidence interval, and we will consider the same distribution with a mean of 10 and a standard deviation of 2. And what we are talking about here applies to any normal distribution. You might have another normal distribution with mean equal to 17 and standard deviation equal to 3.7. The same logic will apply. I'm just using 10 and 2 because the numbers are easy to work with. The 90% confidence interval for a given normal distribution is mu plus or minus 1.65 times the standard deviation. So if you have 10 over here, what this means is that 90% of the data will lie between 10 plus or minus 1.65 s. So if we do 1.65 times 2, we have 3.3. So what this means is the following. 90% of the data will fall between 13.3 and 6.7. 13.3 is 3.3 to the right of 10, which is essentially 1.65 times the standard deviation, and 6.7 is 1.65 standard deviation to the left of the mean. To give you a concrete example, let's say that you are evaluating a stock and the expected return on the stock is 10%, and you know that the standard deviation is 2. That's because the return is not necessarily going to be 10%. It is going to be distributed around 10%, and the distribution is depicted by 2. Given that you have this information and given that you treat the stock return as a normal distribution, what you can say to your boss is that you are 90% confident that the return will be between 6.7 and 13.3%. Similarly, you can say with 95% confidence that the returns will be between plus or minus 1.95 standard deviations of the mean. So this is a more precise number compared to 2, but approximately we can say that 95% of the data will be 10 plus or minus 2 times the standard deviation. So if the standard deviation is 2, we have 10 plus or minus 4. So 95% of the data will be between 14 and 6, and this is what we saw on the previous slide also. And finally, you can say with 99% confidence that the returns will be mu or 10% plus or minus 2.58 standard deviations. Notice that between this slide and the previous slide, here we are using slightly more precise numbers. So even though these also are approximations, but they are better approximations than what you saw on the previous slide. The single most important element to remember is this one. Even though you should also know the 90% number, you should also know the fact that one standard deviation from the mean, so plus or minus one standard deviation, gives you 68%. So these are basic numbers that you can look up from a table, which is what we'll discuss later, but it is important for you to memorize these core numbers. We now will talk about the standard normal distribution. For a standard normal distribution, the mean is 0 and the standard deviation is 1. So this mean, the central point, is 0 and the standard deviation is equal to 1. The standard normal distribution, the random variable, is often denoted with the symbol z. So very often you will hear the term z value. That represents the random variable which is shown on the horizontal axis. You need to learn how to read the probability distribution table, and an excerpt is given over here. The probabilities given over here are cumulative probabilities for a standard normal distribution. Notice that they are calling this x or z. So generally you will see this denoted as a z value. A z value of 0 is this point over here. And notice that the cumulative distribution for a z value of 0 is 0.5. And this should make sense. Given that the distribution is symmetric, that means that half the data will be to the left of the mean. So the cumulative probability for a z value of 0 must be half of 1, which is 0.5. If you go to 0.1, then we are at this point. So with a z value equal to 0.1, clearly the cumulative probability is going to be a little more than 0.5, and that number is 0.5398, and so on. As the z value increases, we will have a higher cumulative probability. So that explains this column. What if the z value is 0.11? Then you use this number over here, and the cumulative probability would be 0.5438. So essentially this means that on the x-axis, if you are at 0.11, so that is your z value, then the cumulative probability is equal to 0.5438. So the first column and the first row essentially are used to come up with the z value, and then the data in the body of this table is essentially the cumulative probabilities. It is important to note that once you learn how to read the table, you should be able to use the fact that the distribution is symmetric. So in my simple example, if I ask what is the cumulative probability with z equal to 0.11, you simply come up with this number. What if I say that you need to come up with the cumulative probability for a z value of minus 0.1? Now clearly this number is less than, this probability is going to be less than 0.5, but over here you don't see any negative z values. So you use the fact that the distribution is symmetric. If you come to this point over here, which is 0.1, then you know that the cumulative probability up till 0.1 is equal to 0.5398, which means that the probability to the right of 0.1 is equal to 1 minus 0.5398, which is equal to 0.4602. Now this 0.4602 is the same as the probability to the left of minus 0.1 because the distribution is symmetric. So the answer to the original question being what is the cumulative probability for z equal to minus 0.1 is 0.4602. Next, we talk about transforming a normal distribution to a standard normal distribution, and you might wonder why this transformation needs to take place. Let us understand this through an example. Say the return on a stock is normally distributed with a mean of 10 and a standard deviation of 2. So you have a mean of 10 and a standard deviation of 2. What is the probability that the return will be less than 11%? So this is your 11% mark, and we need to find the probability that the return will be less than 11%. Now, unfortunately, we do not have a normal distribution table for every single mean and standard deviation. So what we need to do is transform this particular normal distribution. So the normal distribution with mean 10 and standard deviation 2 needs to be transformed into a normal distribution with mean 0 and standard deviation 1. Once we've done this transformation, then we can simply read probabilities of the table. To do the transformation, here is the formula that is needed. You have an x value, and that is what we have over here. For your normal distribution, the one that we are talking about here, the random variable is denoted by big X, and we want to find the probability that this big X is less than equal to 11. So let's do the transformation of this normal distribution into standard normal using this formula. The z value is equal to x minus mu divided by sigma. The transformation of the mean 10, so what does this become? If we plug into the formula, x over here is 10 minus the mean, which is 10, divided by 2. So 10 minus 10 is 0, divided by 2 is 0. So not surprisingly, the mean of 10 transforms to 0, and that is what we expect given the definition of the standard normal distribution. But the more interesting item is 11. So what does 11 transform to? 11 transforms to a z value of 11 minus 10 divided by 2. So this is 1 over 2, which is 0.5, which is essentially saying that 11% on the normal distribution transforms to 0.5 on the standard normal distribution. So the probability that the return is less than 11% is exactly the same that the probability on your standard normal distribution is less than 0.5. And this is something that we can look up on our table. If we go back to the table and we look at 0.5 as our z value, then the cumulative distribution is 0.6915. So for simplicity, let's say that this is 0.69. That means that the probability that the return will be less than 11% is 0.69. And if we are interested in the probability that the return is greater than 11%, then that is simply 1 minus 0.69, which would be 0.31. So hopefully this helps you understand why we need to do the transformation, and the formula that you must memorize is given right here. Let us look at a practice problem now. Assume that the annual earnings per share for a large sample of firms are normally distributed with a mean of 5 and standard deviation of 2. So let us draw that distribution here. We have a mean of 5 and standard deviation is equal to 2. What is the approximate probability of an observed EPS falling between 4 and 5? So what we are saying is the following. There is a certain probability that the EPS will fall between 4 and 5. So this is the probability that we are looking for, the shaded region. In order to solve this problem, we need to do a transformation. We need to transform this normal distribution into the standard normal distribution. 5 transforms to 0, and I will just write down the basic transformation formula. The z value is given by x minus the mean divided by the standard deviation. For a value of 5, you simply do 5 minus 5, which is also the mean, divided by the standard deviation. So that gives you 0, which is what we would expect. What about the 4? The 4 transforms to the following. The x value is 4. What is the corresponding z value? That is 4 minus the mean, which is 5, divided by the standard deviation, which is 2. So we have 4 minus 5 over 2, which is equal to 0.5. So this actually is minus 0.5. So we have minus 0.5 over here. Now we need to find this probability. What we know is that the total probability up till 0 is 0.5. So we need to subtract this probability from 0.5 in order to come up with the probability of being between minus 0.5 and 0. The probability to the left of 0.5 can be determined using the probability table. And again, we use the fact that the distribution is symmetric. If the table you are looking at doesn't have minus 0.5, you can find the cumulative probability for plus 0.5 and then subtract that from 1 to come up with this probability. And we have already done that. Earlier, we noticed that for 0.5, this whole area is 0.69, which means that this area is 0.31. So this area is 0.31, which means that this area over here, given symmetry, is also 0.31. And the area that we are after, which is right here, is equal to 0.5 minus 0.31, which is equal to 0.19. That 0.19 is the same as this area over here. So the probability that the EPS will be between 4 and 5 is equal to 0.19. What we have covered here might seem complicated if you've not seen this material before, but with sufficient practice you will realize that this is fairly mechanical and straightforward. Moving now to multivariate distribution. Multivariate simply means multiple variables. Let's say you have three random variables, A, B, and C, and each of these random variables is normally distributed. And if it helps you understand what we are talking about, say that these three random variables are the returns on three stocks A, B, and C. They are normally distributed. The mean for A is 10, let's say for B is 15, and C is 20. The standard deviation for A is equal to 4, B might be 9, and C, let's say, is 16. So if you combine these three stocks, and let's say that the weightage is equal, then can you come up with the overall mean for this portfolio and the variance for this portfolio? The answer is that yes, we can do that. And the fact that if each individual variable is normally distributed, then the overall portfolio's returns will also be normally distributed, and we can compute the mean or expected value for the portfolio as well as the variance for the portfolio, as long as we know all the means and we know all the variances or standard deviations, and we also need to know the pairwise correlations. So the correlation between A and B, B and C, and A and C. Notice that with three items in here, we need to have three pairwise correlations. In my simple example, n is 3. So if you look at this expression over here, we have 3 into 3 minus 1, which is 2, divided by 2, which is 3. So if you have three variables, then you need to have three pairwise correlations. If you happen to have four variables, say A, B, C, and D, then you would need to have 4 into 3 divided by 2, which is 6 pairwise correlations. And I'm sure you can do a quick analysis here and determine that 6 pairwise correlations will be necessary. So that is all that you really need to know with regards to multivariate distribution. Let us now talk about the applications of the normal distribution. There are two major items. One is mean variance analysis, and the main point here is that when you evaluate a given stock or you are considering an investment decision, you need to think about both the mean or the expected return as well as the variance, which essentially talks about the risk of that particular investment. So when we say mean variance analysis, it simply means that we look at the mean return as well as the variance of the returns before making a decision. The other item we will look at is the safety first ratio, and that will be covered on the next slide. So the main item here is the safety first rule, named after the person who first defined it, called Roy. So this is often called Roy's safety first rule or Roy's safety first criterion, which states that the optimal portfolio minimizes the probability that the return of the portfolio falls below some minimum acceptable level. This minimum acceptable level is called the threshold level. So how do we select a optimal portfolio? What we need to do is come up with the safety first ratio using this formula. If you have a given portfolio and the expected return on the portfolio is equal to 10%, and let's say that you require a return of at least 2%, maybe the inflation is 2% and you want a return more than 2%. One way of putting this is that you want to minimize the probability of the return falling below 2%. So if this is one portfolio and you have another portfolio where the expected return on portfolio 2 is say 7% and your threshold level is still 2%, but let's say that these two portfolios have a different standard deviation. Here the standard deviation is 5% and here the standard deviation is only 1%. So between these two portfolios, which one is safer? And that is what the safety first rule goes after. The safer portfolio is the one where the probability of falling below this threshold level is minimized. So to find that portfolio, we need to first come up with the safety first ratio. Let us compute the safety first ratio for this portfolio. That is simply going to be the expected return on the portfolio, which here is 10%, minus the threshold level, which is 2%, divided by the standard deviation of the portfolio, which is 5%. So here we will have 8 divided by 5, which is equal to 1.6. So the safety first ratio for this portfolio, let's call it portfolio A, is 1.6. The safety first ratio for portfolio B is going to be 7 minus the threshold level, which is 2, and then we divide by the standard deviation, which is 1. So here the safety first level is 5. In order to pick the safest portfolio, we need to go with the one that has the highest safety first ratio. So between A and B, B has the higher safety first ratio, and that is safer. Just to get the intuition behind this, our threshold level is 2%. So clearly the portfolio with the higher expected return is better because it is giving us a larger buffer relative to the threshold level. However, simply looking at the expected return is not enough. We also need to consider the standard deviation. So even though portfolio A gives us a large cushion relative to our threshold level, but the variance of portfolio A is quite high compared to the variance of portfolio B. Here I'm actually pointing at the standard deviations, but standard deviation and variance are interchangeable. So we need to consider both the cushion above the threshold level and the variance. If the variance of standard deviation is high, then that pulls down the safety level, because a high standard deviation implies that the probability of falling below our threshold level becomes more. So that's why we consider both this cushion as well as the variation. We compute the safety first ratio and pick the one with the higher ratio. The one with the higher ratio has a lower probability of falling below the threshold level. Let's see if you can solve this problem now. For a given investor, the minimum acceptable return is 2%. What is the safety first ratio for a portfolio with a expected return of 7% and standard deviation of 10%? So let us just solve this first. You have a situation where the expected return is 7%. So if we just regurgitate the formula first, it's return on portfolio minus the threshold level divided by the standard deviation. So for the first portfolio, the return is 7% minus the threshold level, which is 2%, divided by a standard deviation of 10%. So this will give us 5 over 10, which is 0.5. For the second portfolio, we have an expected return of 5%. So here we do 5 minus 2, which is a threshold level, divided by standard deviation of 6. So we have 5 minus 2, which is 3, divided by 6, which is also 0.5. So it turns out that in this particular example, the safety first ratio is the same. So we can actually pick either one. In both cases, the probability of falling below the threshold level is the same. See if you can solve this practice problem now. The solution is given on the next slide. Here is what you should have come up with. The answer is C, and this is the safety first ratio, which is higher compared to the other portfolios. The log normal distribution. The log normal distribution is generated by the function e to the power of x, where x is normally distributed. If you take this normal distribution, where x is the random variable, and you transform the normal distribution by taking e to the power of x, so x is a normal distribution, what you end up with is a log normal distribution. And the way you can think of this is, if this is 0 and this is minus infinity, so minus a big number, when you do e to the power of a minus number, especially if this minus number is big, then you will essentially have something that is close to 0. You can never have e to the power of something that is a negative number. So this log normal distribution is bounded by 0. And just as an experiment once in your lifetime, you can actually try to do this. Take different numbers of x, starting from minus some big number like minus 100, and then go all the way to 0, and then take some larger numbers like 10, 12, and so on, and you will get a distribution that looks something like this. So this is your log normal distribution. From an exam standpoint, there are some basic points that you need to remember. The first one is that the log normal distribution is bounded from below by 0. So it is useful for modeling asset prices which never take negative values. So if you are modeling an asset price, obviously the lowest an asset price can go to is 0. Therefore, it makes more sense to use a log normal distribution versus a normal distribution which can take on negative values. When you are modeling returns, returns can be negative, so it is okay to use a normal distribution to model returns. Clearly, the log normal distribution is skewed to the right, so you see a fatter tail over here. And remember the phrase, the log is normal. So what that means is, given that this is e to the power of x, the log normal distribution, if you take the natural log of e to the power of x, you simply get x. So that is basic log mathematics. So the log of the log normal is x, which we already defined as a normal distribution. So the log of the log normal distribution is normal. That's why we say that the log is normal. And finally, we will talk about the Monte Carlo simulation. What you need to do is simply read what is given on the slide. I will give you a very basic explanation of how this works, but make sure you read this first. Let us say that you are trying to price a complex security, and you have a certain model for pricing that security given different factors. So let's say the first factor is interest rates. You can expect different possible interest rates in the future. That's one factor. Similarly, there might be other factors. Let's call them factor 2, factor 3, and so on. Then there is a certain model that you apply, and you come up with the price of the security based on the model. What Monte Carlo simulation allows us to do is predict or project different possible values for the interest rate. So you tell your computer system, which is where the simulation is going to happen, that for interest rates you are expecting a certain value of say 4%, and there is a certain distribution. So you feed this distribution into the computer. Similarly, you feed the distributions for factors 2 and factors 3. So whatever you feel the appropriate distribution might be, you enter all this into the computer. What the computer then does is takes a particular value for the first factor, a particular value for the second factor, and the third factor, assuming that we just have 3 factors over here, and obviously we could have more. And then based on these factors and the model that is specified in the computer, it comes up with a certain price. Then it runs a second iteration where it will take another possible value for the factor based on the distribution, another value for factor 2, another value for factor 3, and it will come up with another possible price. And it will do this 1,000,000 times. And based on running this, say 1,000,000 times, there will be a certain distribution for the price. And essentially, by running millions or thousands of iterations, we will get a certain distribution for the price of our complex security. Now, as long as you understand the general concept, you are fine for the exam, because clearly you will not be required to do a Monte Carlo simulation on the exam. In the real world, though, this is a technique that is used very often, because in the real world you will have access to the technology that allows you to do such simulations. From an exam standpoint, you need to understand the limitations of the Monte Carlo simulation as well as the limitations of a historical simulation. The Monte Carlo simulation is what we've just talked about, and you simply need to read what is on this slide to understand the basic limitations, the sorts of models that we just talked about. So just understand what we mean by a historical simulation, and the limitations are quite self-evident. You can read what is given on the slide over here. So we are now at the end of this reading. Just a brief summary. The most important points are that you need to understand the basics related to the distribution of discrete random variables and continuous random variables. With a discrete random variable, you can either have a uniform distribution, and here you can think of the example where we said let's roll a dice, and there are 6 possible outcomes, each with a probability of 1/6. So uniform because each outcome has the same probability. With a binomial, remember the fact that we have a combination of Bernoullis. The binomial distribution essentially deals with the probability of success. So to quickly summarize this point, let's say you flip a coin 10 times. The probability of being successful 7 times would be an example. So 7 is your binomial random distribution. The formula that you need to remember is NCX, where N is the total number of times you perform the experiment, X is the number of successes, and then P, which is the probability of success, to the power of X times 1 minus P to the power of N minus X. This is the probability of having 7 successes. Then you also need to remember the expected value is N times the probability, and the variance is N times the probability of success times 1 minus P. Then we moved on to continuous random variables. So here we are simply saying that between a bound of A and B, a continuous random variable can take on a value, and the probability of being within any small range is the same as long as this distance is the same. And then we spent a fair amount of time on the normal distribution. You need to memorize the critical formula, which is Z is equal to X minus mu over the standard deviation. Plus you need to also remember the area under the curve for 1 standard deviation from the mean, 2 standard deviations from the mean, and so on. And you need to learn this transformation and practice several problems. Just to conclude, as I keep saying, you need to go over the learning objectives presented in the curriculum. go over the examples, but these examples in the curriculum can be fairly complex. So if you find them difficult, don't worry too much. Just read them once or twice. Also, the practice problems in the curriculum, some of them can be complex. Read the solutions. But for this particular topic, I would say that you practice problems from Schweser or FinQuiz or other sources to get a better sense of what you will eventually see on the exam. That is it for this reading.